In this video, I'd like to tell you something about the contact process. Let us start with a stick man. This stick man will get sick, and we will give him 2 neighbors for him to infect. We will need to make some assumptions about how this model works. We will assume that an infected site heals randomly, on average 1 time per second. An infected site will also infect its neighbors randomly, lambda times per second per neighbor. The specifics of the model are not important right now. I want to show you something that happens in this contact process. If we simulate the model with an infection rate 2, we will see that it takes a very long time for these 12 stickmen to recover. If we now instead move to the same model, but now with an infection rate equal to 1, we will see that very quickly these stickmen will all recover. This hints that there might be a fundamental change in the way the model behaves if we go to a specific value somewhere between this rate 1 and rate 2. What I've just shown you is the contact process on Z with infection rate lambda. And there is such a critical value where this change occurs. And this value we call lambda C. Below this critical value lambda C, the infection surely dies out. But above this value, the infection has a positive probability of survival. The goal of this video will be to show that the critical value is greater than 1/2. To do so, we will look at something seemingly unrelated, namely family trees, which randomly generate. And then we will go into more detail with the contact process to finally connect these two to get to our goal. Let's start with the family trees. We will look at the family tree, and specifically we will look at the male line. This is because historically this is the line who carries the family name. We will start with a single node and do what is called the Galton-Watson process. This is a way to randomly generate a tree, and we do so by constantly sampling one distribution which is identical and independent for each node. That means that each node has the same probability of getting a certain number of children, regardless of what happens in the rest of the family tree. If we start with Edward, we sample this X to get 2 children. And now, for each of these children, we will again independently and identically sample new children. So Edward gets 1 child, Henry gets 3. We continue like this for all nodes, and what might happen is that we just get 1 more child in this tree and then it dies out. One thing that is useful to think about with Galton-Watson process is so-called generations. For example, this is the 2nd generation, which is exactly what you would expect in the context of family trees. Now that you know what the Galton-Watson process is, I want to prove a relatively simple fact about it. Let Zn be the number of individuals in the nth generation. We will now look at the expectation of Zn, and we'll specifically condition on how many sites there are in the previous generation. So we look at all possible number of children there can be in the previous generation with the associated probability and sum over all of those. If we do so, we now get a conditional expectation that's relatively easy to compute. If we know that in the previous generation there are m individuals, we know that each of them will generate new children according to x. So the total number of expected children after this step will be m times the expectation of x. Now we can recognize that we've once again got an expectation, which is m times the probability that Zn minus 1 is m, and then the sum over all of those, which if we take that out, we see that this expectation of Zn is equal to the expectation of x times the expectation of Zn minus 1. This we can repeat inductively, and so we see an interesting relationship between Zn and e to the x. We can now use this relationship to prove a very tangible fact about these trees, specifically about the extinction of these trees. We can now use the Markov inequality. This allows us to relate this probability that Zn is greater than 1 to its expectation by an upper bound. And since we know that the expectation of Zn is equal to the expectation of x to the n, we can substitute that in, and taking the limit, we see that with the expectation smaller than 1, this limit goes to 0, which proves that the nth generation will surely be empty as we let n grow large enough. This now essentially means that the tree must die out. If the nth generation is 0 at some point, that means there are no further generations, so the tree has died out. This means that if the expectation of x is smaller than 1, then extinction occurs with probability 1. Now that we've established this first fact about family trees, we're almost ready to go to the contact process. But I first want to show you something about the exponential distribution. The exponential distribution will be essential in defining what the contact process is. So it's important that you understand one interesting fact about it. If we look at the probability that x is greater than t, that corresponds to this area under the distribution curve. Now, I want to relate this to another probability. Namely, if we've already waited s seconds, I want to know the probability that we have to wait another t seconds. To get this conditional probability, we need to adjust this curve a bit, because if we've already waited s second, s is really our time 0, so we have to shift our distribution to this time 0. Now, the total area under a curve is no longer equal to 1, so we have to readjust the curve to fix that problem. And now what you see is that this probability that we have to wait s plus t seconds, given that we've already waited s seconds, is exactly the same as the probability that we had to wait t seconds. This is a crucial fact, and it's what's called the memoryless property of the exponential distribution. We're now ready to look at the contact process. The contact process is just a set of infected nodes at a time. We will say that every infected node heals after a time sampled from the exponential distribution with rate 1. Additionally, we say that each infected node will infect one of its neighbors after a time sampled from the exponential distribution of rate lambda. You can also say that healings occur at rate 1 and infections at rate lambda. Now that we also know about the memoryless property of the exponential distribution, we can introduce something called the Markov property. The Markov property states that the future of the process is only determined by what the state looks like right now. You can make sense of this by thinking that all of these exponential rates don't get influenced by how long they've been waiting. So if you know what sites are infected, that's enough information to determine the future. Now I want to give you a more visual way to think about this contact process. I've drawn a diagram with on the x-axis nodes and z, and on the vertical axis we see time. Some people might already know about the Poisson process, but it's just a way to model events where the times between them are exponentially distributed. We can use such Poisson processes to draw infection errors on our chart. You can think of these as potential infections from one node to another. And because we've used this Poisson process, the times between all these arrows are exponentially distributed. We can add the healings in by adding blue pluses, again with a Poisson process with rate 1 times between the events. The interpretation of this diagram is now that a site is infected at a certain time if there exists a path from an initial infection, in this case 0, to this site. For example, we can see that there's a path from 0 to -1 at time t. So -1 is infected at time t in the contact process. With this visual representation, we're now almost ready to get into the main proof of this video. But I want to quickly delve into the critical value I showed you at the start. Remember this change in behavior that happened in the process. This change in behavior we can quantify using this definition of the critical value. The specific mathematical notation is not very important. I just want you to realize that to show that the critical value is greater or equal to 1/2, we have to show that the contact process surely dies out if lambda is smaller than 1/2. This is what we'll do now. We have once again our diagram which shows the contact process, and we will compare it with a certain family tree. Let X be the number of infected sites after one infection or recovery. That means the number of children in our Galton-Watson tree will be the number of infected sites after either one infection has happened, and so now there are 2 infected sites, or one recovery has happened, and there's no sites left. Let's look to an example. If we start from 0 and we do the first step, we see that the first event is an infection. So we will get 2 different neighbors in our Galton-Watson tree. Next, we go to the first child in this tree and we see that again, the first event is an infection. So once again, we add 2 children. The same holds for this next event. And now we continue with the next generation. Starting with the leftmost child in the second generation, we come across a blue plus, which means the site recovers and the child has no children. We once again get another infection, and then something interesting happens. Remember from the Galton-Watson trees that we had to generate children identically and independently from the process. So this third node is going to overlap a path we've already been through, which we cannot do because we cannot generate nodes in the same way as another node in this generation or in the tree for that matter. To combat this, we will say that any node that comes across a path where we've already been will from now on generate independently, but according to the same distribution, so we still get a Galton-Watson tree. The final node will now again generate according to our process, which gives us 2 more infected nodes. We can continue like this with the next generation, and we see that the first node goes off of our picture, but will generate more nodes further down the line. And the second node once again crosses our path, which is not allowed. So we will now generate the rest of the nodes from this branch onwards, independently from this contact process. We can continue like this to get something that looks like this for the final tree. I want you to take a moment to realize what we've done here. We've made a connection between these 2 processes that ensures that once the Galton-Watson process dies out, the contact process must die out too. Since our Galton-Watson process really walks through the entirety of this visual representation of the contact process that can be accessed from an infected node. This means we just have to show now that our Galton-Watson process dies out if lambda is less than 1/2. To do so, we need to determine this expectation we had. By the virtue of our distribution, the expectation is simply 2 times the probability that there's an infection before a recovery. We can determine this probability just by looking at the rates of infection and recovery. We can see that we affect our left and right neighbor both at rate lambda, so the rate at which we infect any neighbor is equal to 2 lambda. We will denote this by y. Now, the rate of recovery is equal to 1, so we have another random variable z, which is exponentially distributed with rate 1. Now, this probability is just a probability that y is smaller than z, and a short calculation will give you that this probability is equal to 2 lambda over 2 lambda plus 1. This now gives us that our expectation of x is equal to 4 lambda over 2 lambda plus 1. We can now finally do some simple algebraic manipulation to show that this is exactly smaller than 1 if lambda is smaller than 1/2. Thus, the contact process dies out as lambda is smaller than 1/2. After a lot of work, we can now finally reach our desired conclusion, that the critical value of lambda is greater or equal to 1/2. I want to thank you very much for watching this video. This video gave an impression of the results I obtained during my bachelor thesis in mathematics. If you want to read more, you can find a link to it in the description. Don't expect any earth-shattering results though. Now, I hope you have a nice day.